Hello and welcome to Umehluko Science Revision. My name is Dr. Douglas and I will be your host for today. This is the third lesson in a series on acids and bases. And in today's lesson, we are going to consider the following topics. We're going to look at the pH scale. We're going to look at the concept of Kw and the autoionization of water. Kw is the equilibrium constant for the autoionization of water. And you have encountered equilibrium constant of reactions in a previous video. Ka and Kb, those are equilibrium constants for acids and bases. And we will see in more detail exactly how this works. Finally, we will look at how pH, conductivity, and the reaction rate depends on whether an acid is a strong or a weak acid, or a strong or weak base, and depending on the concentration of the acids and bases. Right, so let's get to this. So first of all, we will look at the pH scale. So what is the pH scale? pH is a measure of the acidity or alkalinity of a solution. pH comes from a German word, and it is potens hydrogen, pH. Now, according to the Bronsted-Lowry model, an acid is a proton donor and a base is a proton acceptor. And the hydrogens, these are the protons that are in our solution. And the greater the pH, the lower the concentration of hydrogen or hydronium ions are, and the lower the pH, the greater the concentration of hydronium or hydrogen ions are. So acids will increase the hydronium concentration and decrease the pH, while bases will decrease the hydronium concentration and conversely increase the hydroxide concentration and therefore increase the pH. The concentration of the hydrogen ions, and there's an equation for this, which we will see now, tells us whether a substance is acidic, basic, or neutral. When the pH is 7, the solution is neutral. When the pH is greater than 7, the solution is basic. And when the solution is less than 7, the pH is acidic. The equation we use is the following. We say that the pH is the negative log of the hydrogen or hydronium concentration. So we can write either hydrogen concentration or proton concentration and hydronium concentration. They mean the same thing. And so we can also write it in this form. We can say that the pH is the negative log of the hydronium concentration. In water at 25 degrees, in neutral pH with pure water, we see that the product of the hydronium concentration and the hydroxide concentration has a specific value, 1 times 10 to the minus 14. And this can be used to determine our hydronium concentration. Let's look at an example. So here we've got this problem statement in a 162 cubic centimeter solution of ethanoic acid. The following equilibrium is established. CH3COOH plus H2O. This is a reversible reaction, forms CH3COO minus ions and hydronium ions. The number of moles of CH3COOH is found to be 0.001 mole. Calculate the pH of the solution. So to find the pH of the solution, we need to find the concentration of the hydronium ions. Now, how do we do this? We do this by looking at our balanced equation and by looking at the mole ratio that's given here. They give us the volume of the ethanoic acid, and so we can use that information as well. So, if we look at the mole ratio of the ethanoate ion to the mole ratio of the hydronium ion, we notice that it is 1 to 1. So the number of moles of the ethanoate ion is the same as the number of moles of the hydronium ion. So we can, by knowing the amount of the ethanoate ion, we can then find the amount of the hydronium ion. Right, so it tells us the number of moles of CH3COO minus is 0.001 mole. Calculate the pH of the solution. We can therefore say that, well, the number of moles of the hydronium ion is also equal to 0.001 mole. But we don't want the number of moles, we want the concentration of the hydronium ions. And once again, if we look at this equation, we can see that the mole ratio of the ethanoic acid to the hydronium ions is also 1 to 1. And so we can use the volume that's given here to be able to work out our concentration of our hydronium ions. We can't use cubic centimeters, we must convert to cubic decimeters. So the volume that we've got is going to be 162 divided by 1,000, which is 0.162 cubic decimeters. And therefore, the hydronium concentration, which I'll write with the square brackets like this, will be equal to the number of moles per unit volume, and therefore it will be 0.001 mole divided by 0.162 cubic decimeters. So the answer to this is going to be 0.006 mole per cubic decimeter. What we can now do is we can take this value and substitute it into our equation for the pH. And so let's do that. Our equation pH is the negative log of the hydronium concentration. So that's minus the log of 0.006. And the answer to that is the following. That gives us an answer of 2,22. Therefore, pH has a value of 2,22, which you can see is acidic, which is what you'd expect because this is an acid that is in solution. Now, water is a very interesting substance in that it ionizes by itself to a very small extent. So if we have this reaction here, we have water reacting with the water, and this is a very reversible reaction to form hydronium ions and hydroxide ions. So one water molecule can donate its proton to the other water molecule. The other water molecule then will become a hydronium ion, while the original water molecule will have lost a proton and therefore becomes a hydroxide ion. So this reaction, where the proton is transferred between identical molecules, is called autoprotolysis. Autoprotolysis, auto meaning self, proton meaning proton, and lysis meaning cut. So this is the autoprotolysis or autoionization of water. Because this is a chemical reaction, it also has an equilibrium constant called Kw, and Kw is written as follows. Remember, how do we write the equilibrium constant for a chemical reaction? We say that the constant is equal to the concentration of the products divided by the concentration of the reactants. And in this example, both of the reactants are in the liquid state. So we don't include their concentration in this reaction. So what we can say is that this is just the concentration of the products, and therefore it's the concentration of the hydronium multiplied the concentration of the hydroxide. And at 25 degrees Celsius in pure water, the Kw is going to be 1 times 10 to the minus 14, because at 25 degrees, the hydronium concentration and the hydroxide concentration are the same. And they both have the value of 1 times 10 to the minus 7. We will use this in calculations going forward. With an acid-base reaction, we are also able to write a equilibrium constant for the acid and base reactions. Just as for a normal reaction, we can write Ka as the equilibrium constant for an acid and Kb as the equilibrium constant for a base. And this is for the ionization process of an acid and for the same dissociation or ionization of a base. And this determines whether the acid will be weak or strong. Let me repeat that. The Ka and Kb value indicates whether an acid is weak or strong because it reflects the amount of ionization or dissociation that takes place in an acid or a base. Let's see how this works. For the example of a strong acid. So hydrogen bromide is a strong acid. Let's look at the ionization reaction for hydrogen bromide. So we've got hydrogen and bromine as a gas, react with water as a liquid. It's a strong acid, so therefore we've got hydronium ions. The hydrogen bromide donated its proton to the water, and then we've got bromine ions in solution. We notice that the arrow here points one way. This tells us that this is not a reversible reaction. Let's calculate a value of Ka, and first of all, let's write an expression for the equilibrium constant of this acid ionization reaction. So if we look at this, we see that it's the concentration of the hydronium multiplied by the concentration of the bromine, because those are the products, divided by the concentration of the hydrogen bromide. We don't include the water because the state of the water is liquid, and therefore we don't include that in our calculation. So when we calculate this under experimental conditions, we find that this is a very, very high number, 1 times 10 to the 9. That's 1,000 million, which is a very, very large number. And what that says is that the number on top, in other words, the concentration of our products, is much greater than the concentration of our reactants. And this is what we expect. Remember that a strong acid dissociates or ionizes almost fully, and therefore there will be a very small concentration of the original molecules left, while there will be a very large concentration of the resultant ions. And this is exactly what this value tells us. So what we can then see is that the reaction equilibrium lies far over to the right. We have a very large arrow and a very, very small arrow going to the left. What this means is that the hydronium ions do not give off their proton back to the bromine very easily. And therefore, the reverse reaction is very, very small. So, in fact, there is an equilibrium, but the equilibrium lies very far to the right, which is what we expect for a strong acid. For a weak acid, let's consider the following situation. Ethanoic acid is a weak acid. And when we look at the ionization of ethanoic acid in water, we can see that hydronium ions are formed and ethanoate ions are formed. Now notice that the reaction is reversible. The arrows point both ways. When we work out the Ka value for this under experimental conditions, we find that it is of the order of 1.7 times 10 to the minus 5, a very, very small number. What that means is that the concentration of our products is very, very small, and the concentration of our reactant is very large, which is to be expected because we know that a weak acid is one in which the molecules ionize to a very small degree, and that is shown in this equation here. And in fact, if we had to draw the equilibrium, we see that the equilibrium lies far to the left because all of our, say, most of our original molecules did not ionize in water. We can do the same analysis for bases. So for a strong base like sodium hydroxide, here we've got sodium hydroxide in water, and this forms sodium and hydroxide plus water in the reaction. Remember that the Kb is then the ratio of the concentration of the products to the ratio of the concentration of the reactants. Water is a liquid, so it does not appear in this reaction. And because NaOH is a strong base, the equilibrium lies very far over to the right. You can see the arrow is very large. That means that the concentration of our products is going to be much less than the concentration of our reactant. In other words, there are very few NaOH ions left in the reaction. They've all dissociated to form sodium ions and hydroxide ions. For a weak base, like ammonia in water, this is the reaction. Once again, writing the Kb value for a weak base, you see that this is of the order of 10 to the minus 5 because it's a weak base. That means that the concentration of our products at the top is much less than the concentration of our reactants. In other words, we have many or high concentration of ammonia, and not a lot of it has dissociated to form the product, and therefore the reaction lies further to the left, and we can actually write this as a reversible reaction because we have a weak base in this case. Let's do a worked example on calculating the equilibrium constant for an acid or a base. Right, so here we go. Calculate the equilibrium constant for hydrochloric acid added to 1,38 cubic decimeters of water. We look at our reaction here, HCl plus H2O. This is the ionization reaction for HCl. We see that we form hydronium ions and chloride ions. Right, so what we want to do is we will follow the following steps. First of all, we'll calculate the concentration of the HCl at equilibrium. We're given the fact that the number of moles of HCl in solution is 0,005 moles, and the number of chloride ions in moles in the solution at equilibrium is 87,3 moles. So let's work out the concentration of HCl at equilibrium. So the concentration of HCl is the number of moles divided by the volume. So that's 0,005 divided by 1,38, and that gives an answer of 0,0036 moles per cubic decimeter. Right, now we want to find the concentration of the chloride ions at equilibrium, because we'll use this information when writing the equilibrium constant equation. Right, so the concentration of the chloride ions, because that's going to be our product, will be the number of moles of chloride ions divided by the volume. That's going to be 87,3 divided by our volume of 1,38, and that will give us an answer of 63,3 mole per cubic decimeter. And we notice once again that our number of moles of HCl in solution is very, very small because our HCl has almost completely ionized. We have a large number of chloride ions, 87 moles, which also bears out that fact. Right. Let's find the calculate concentration of the hydronium ions at equilibrium. And we do that by looking at the mole ratio of our hydronium and our chloride ions. So we see that the mole ratio of our chloride ions to the mole ratio of our hydronium ions is 1 to 1. We look in front there, it's 1 to 1. So it's 1 to 1 as a mole ratio, and therefore we will have the same number of moles in the same volume, and therefore the same concentration of hydronium ions in our final solution. Right, so now let's calculate our Ka, and to do that, we need to write an expression for the equilibrium constant of the acid. So Ka is going to be the concentration of the products divided by the concentration of the reactants. So that's going to be the H3O plus times the Cl minus divided by the concentration of the HCl. Note that HCl is aqueous, hydronium is aqueous, chloride is aqueous, so we include their concentrations, while the water is liquid, so we don't include the concentration of the water in our Ka expression. Can now substitute our values in. For this is going to be concentration of hydronium, which is 63,3, multiplied by the concentration of the chloride, 63,3, divided by the concentration of HCl, 0.036, and that will give us an answer of 1.11 times 10 to the 6. You can see that 10 to the 6 is a very large number, which is what we expect because HCl is a strong acid. Finally, we are going to look at the effect of pH, the conductivity, and the reaction rate on different acids and bases. So if we look at this here, this is a strong acid dissolved in water, and it almost fully ionized to form the hydronium and the metal ion. We can see here in here, these are all, there are none of the original molecules left, and this gives us a very low pH, as we expect, because there's a high concentration of hydronium ions. These ions in here, those are hydronium ions. There's a large concentration of that, and therefore we expect the pH to be small. When it comes to the conductivity, because there's such a high concentration of these ions, that means that in solution, they are able to be carrying the charge that they have in the solution, and a large amount of ions means a large amount of charge, and therefore a high conductivity. In terms of the reaction rate, we are going to look at the particle nature of matter, and remember from a previous lesson, we said that the reaction rate depends on the number of effective collisions. And if we have a high concentration of ions, that means we can have a high rate of effective collisions because there are many particles that can collide effectively, and therefore there will be a high reaction rate for the reaction of a strong acid with a metal hydroxide, a base, and so on. For a weak acid, we can see that the opposite is true. So for a weak acid, we notice that there are still some of these acid molecules that are in the solution. It means that not all of the acid molecules have ionized to form the hydronium ions, and therefore the pH is a little higher because the concentration of hydronium is not as great. Because we have a smaller amount of ions and more molecules that are neutrally charged, the conductivity of this solution is much less because there are fewer charge carriers that can put charge into the external circuit. Also, since there are fewer ions, that means that the number of effective collisions will be less, and therefore the reaction rate of a weak acid with a metal hydroxide, metal carbonate, or a base will be less than the equivalent concentration of a strong acid. And the same sort of argument can be made for a base. To show briefly here, these are the base ions. There are no base ions in the solution because they've all dissociated to form our hydroxides. We've increased the hydroxide concentration, therefore decreased the hydronium concentration, and this gives us a high pH for the strong acid. Because we have a large number of ions, we have a high conductivity because many charge carriers are available in the circuit. And finally, in terms of the reaction rate, because we have a large number of ions, we have a large number of effective collisions, and therefore the reaction rate with a strong base will be very high. For a weak base, the opposite is true. In a weak base, we still have some of our base molecules in the solution. Not all of them have gone to form hydroxide ions, and therefore the pH is slightly less. It's still above neutral because we have more hydroxide ions in excess, but it's less than in the case of a strong acid, because a strong base, because a weak base did not dissociate or ionize fully. In the same way, fewer ions are available as charge carriers, and therefore the conductivity of a weak base would be lower than that of a strong base for the same concentration. And in terms of the reaction rate of a weak base, fewer particles that can react mean fewer effective collisions, and therefore a lower reaction rate. Thank you very much.